So the second that is less obvious is what happens if you have a three-dimensional surface over which inviscid streamlines diverge or converge from each other. Right. For example, if you just have a, let's say, axisymmetric body, let's say something like a submarine. Okay. So near the leading edge of this axisymmetric body, the streamlines has a divergence. They move away from each other, even if you look at the inviscid flow. And near the trailing edge, the streamlines converge towards each other. What kind of effects do you think this kind of divergence and convergence of streamline has to do with the boundary layer? Another way to ask is that if I can measure the pressure distribution over this submarine, and I can match the same pressure profile with an airfoil. So let's say this is 3D, and I can match the same velocity profile with an 2D airfoil. Okay, how is the development of the boundary layer different between the axisymmetric 3D case and the 2D case? So let's first focus on the leading edge. Okay, you can discuss with each other, but like the first question is the 3D shape have a more rapidly developing boundary layer or less rapidly developing boundary layer? Is it thicker or thinner? Right, but what I'm saying is if you have the same pressure distribution.
Right, along the streamwise.
Yeah, along the streamwise coordinate,
right,
between the 2D and 3D case. Okay, so let's first look at the equations, the mass conservation equations. Plus partial v partial y equal to 0, right? This is the 3D equation, and the 2D equation is partial u partial x plus partial v partial y is equal to 0. This is 2D. Okay. Now, what's the difference? The right hand side are both 0, right? What's the difference in the first term and the second terms in these two equations?
dw by dz.
Yeah, there is a dw by dz in the first case, which is positive or negative. So if you think of the x direction as going downstream in both cases, and here the z direction would be that way.
Circumferential.
Yeah, z direction is circumferential. Should be doing that.
It's 0 because that is.
Okay, right. So yeah, so if you define z as right, so okay, so if you define the coordinate like that, dw by dz is actually 0. But like here, if we define the coordinates locally so that they are always orthonormal to each other, okay, then what you have to do is, let me actually write it, illustrate it more clearly that way. So this is the surface. This is what the surface look like, and you have a, this is like the leading edge. You have a surface that goes out like that, right? Okay, so this is my leading edge, and you have other. This is the nose of my submarine. And if you define a coordinate system that has to be always orthonormal, that means not only they have to be orthogonal, but also the coordinates has to be of the same length. The dx and dz has to be the same. then what you have to do is you have to, when you move in the x direction, your delta z now has to be exceed what this is, right? So your coordinate has to be like that, and when you move further upstream, it has to be like that, right? So your coordinate has to be something like this. It can no longer confirm. So your z direction can no longer conform to these perfectly axisymmetric lines. Now, if you think about this, what is my partial w partial z? So let's say this is x, this is z, and if you do this, the w is defined in this direction. The w is defining, sorry, the w is defined, the u is defined in this direction, right? And w is defined by whatever that is different. So if the q is in this direction, then you have a positive w here. And if q is in this direction, you have a u in this component and a w in this component, right? So your dw by dz has to be what? Greater than 0 or less than 0? Has to be greater than 0, right? It contributes to a positive divergence on the surface, right? So do you agree that if you have a flow, so if you look from the front, right? Let's say this is my axisymmetric body looking from front. You're going to see the streamlines go out like that, right? Does this look like a positive or negative divergence for you on this two-dimensional surface? It's a positive divergence, right? So, and this is the contribution from dw dz. Even if du dx doesn't, even if u velocity doesn't change along the streamline, you still have a positive divergence. So dw dz is positive in the three-dimensional case. And what does it mean for dv dy then? Yeah, dv dy has to be less than that in 2D. So imagine, I mean, one of the ways to think about it is imagine the x velocity profile is not changed at a particular location, right? Then du dx is the same and dw dz has to be positive. So dv dy has to be less in the three-dimensional case. It may even be negative if dw dz is large enough.
So why does du dx have to stay the same?
It doesn't have to be the same, right? I'm just thinking of a hypothetical thought experiment. So, or imagine if you start solving a differential equation, a time-dependent differential equation, starting from a boundary layer profile that conforms with the two-dimensional airfoil case, right? How would it evolve? In which direction would the boundary layer evolve? What happens is that the divergence equation has to be satisfied. Therefore, at the first moment, your dv dy has to be different, has to be less than in the three-dimensional case. And v is 0 at the surface. That means your v in the three-dimensional case is going to be smaller. Or you don't have as much velocity in the three dimension that goes from the wall to the free stream. As a result, your velocity direction is going to be less tilted towards outside, right? Your velocity direction is going to be tilted more horizontally or even downward towards the wall, possibly. What does that mean? That means your boundary layer wouldn't be growing as fast, right? So if you look at a two-dimensional profile, you have velocity that is slightly going upward, And if you look at a three-dimensional profile, the velocity, just to take an exaggeration, may even going downward. Right? So as a result, the growth of the boundary layer is a combination of two effects. One is the y velocity, is the v, right? That actually advanced the slower velocity upward. Another effect is the shear that, due to viscosity, brings the velocity slower, even at the same streamline. So in the 3D boundary layer, the advective effect of the thickening of the boundary layer is less severe, or even the opposite effect, because of the divergence in the lateral direction. But if you have convergence in the lateral direction, like in the trailing edge, the effect is opposite, right? Because in the third dimension, the flow converges. That has the effect of pushing the flow outward. Right, so if you have streamlines, let's say over here, that converges, like, think of like a tornado, right? So if you have streamlines converging to the same spot, the only place where the flow can go is upwards, right? So if you have a converging streamlines, then the y-directional velocity is going to be higher, and that tends to thicken the boundary layer by advecting the slower velocity from inside the boundary layer to outside. While if you have diverging velocities, that has the same effect as like sucking flow from the boundary layer. So the velocity tends to be more going downwards, and that slows the growth of the boundary layer. Yeah, you can do body aligned grid like the green one, but then the definition of divergence has to be different.
Right. Okay,
So
then the divergence would be included in the definition of the grid itself.
That's right. That's right. That's right. So if you the divergence is always defined in a way that you can apply the divergence theorem, right? So if you integrate the divergence, the integral of the divergence over a surface has to be equal to the, in the two-dimensional case, equal to the integration along the boundary of the surface of the outward normal times the vector itself. So you have to define it in a way that is consistent with the divergence theorem, and that has to be independent of whatever coordinates you choose. All right.
So divergence has thinning effect, whereas convergence has thickening.
Thickening effect, yes. Okay.
Well, so when you said it was diverging,
Yeah.
or converging, there's the. Oh no, you said there's when it's converging, there's a sucking effect.
When it's diverging,
Yeah.
it means you have a positive contribution here, right? So if you move that positive contribution to the right hand side, that is like you have a negative source term in the divergence in the mass conservation equation, right? If you focus on just on 2D, if you move the z directional derivative to the right hand side, then the left hand side is like a two-dimensional mass conservation equation, and the right hand side is negative. So it's like you have a 2D equation, but then something sucks your mass.
2D with a sink.
Yeah, it's basically like 2D with a sink. In the converging portion of the geometry, it's like a 2D equation with a mass source.